So in this first session we have two talks. Our two faculty leads are Dan Cox, who's a professor in physics, who leads the Answer Rise theme. He's going to come up first and introduce their theme, and then that'll be followed by Tom Turrentine, who is the director of the Plug-in Electric Hybrid Vehicles Centre. So Dan, if you'd like to come up first.
Thanks very much. And I do want to thank the Chancellor and the Provost, who just stepped out for a second, and Harris, for instituting this program, which is really, I found an envy of all my colleagues at other universities. It's a great idea. It's supposed to be good for me, I gotta say, and for our group. Our group's name is Answer, amyloids for nanoparticle synthesis, energy, and radiation, wiring and radiation. Sometimes you come up with good acronyms and you forget what they mean. So basically, the bottom line idea is this. We want to take amyloids, which of course cause all kinds of problems when they stick together in our brains and things like Alzheimer's disease and mad cow, but turn them into essentially molecular Legos that could be used for green manufacturing and growing devices and materials that could be useful, for example, for energy applications. And of course, as was already discussed, some of our best products really are our students. And one of the students we're most proud of is Maria Del Refugio Peralta. Maria grew up in San Jose and got her undergraduate degree at St. Mary's College, and then she worked for 2 years in industry at SP3 in Silicon Valley, and then she came here a few years ago. We were happy to attract her to work on this program, and she's going to tell you about it.
Thank you, Dan, for that introduction. So like he said, my name is Maria Peralta, and I am a graduate student in Michael Toney's lab. And so I'm just going to give you a quick introduction to our overall project. And like Dan says, our overall project is really summarized in the acronym ANSWER, which stands for Amyloids for Nanoparticle Synthesis, Wiring, Energy, and Remediation. The overall goal of this project is really to be able to synthesize and put together a programmable protein-based self-assembly scaffold that can really be programmed on the nanoscale. So being somewhere between the 2 and 20 nanometer scale. And that's really something that hasn't been done in literature before. And so here's a quick schematic of what we hope to accomplish. So we have a protein here, and it normally stands on its own, so just a monomeric protein. If we can go in and do some protein engineering so that we make this protein that is normally by itself form a protein polymer under very benign conditions. And so if you imagine if we have this protein polymer that then we, on one side, we can attach to a specific substrate of choice, and on the other side, we can then functionalize it with a few different things. So here I'm specifically showing a nanoparticle binding peptide. And so these peptides have been shown in literature to bind nanoparticles. And we can then attach a peptide, or with further reduction, form a nanowire that can then be used for various different applications, such as thermoelectric devices, solar cells, and enzyme arrays. And so we actually went ahead and did this for 2 different proteins. Here I'll be highlighting one of them. And this is sort of the protein design scheme that we undertook. So we took a protein that was found in nature called SBAFP, and this protein is found in the spruce budworm insect, and its natural function is an antifreeze protein. So it helps the insect survive sub-zero temperatures. This protein is highly regular structure. It's very repeatable, as you can see here, except until you get to the end of the protein. So right at the C-terminus, the protein, which is highlighted here in red, begins to fold back on itself. And this serves as a capping motif, which would prevent any protein polymer from forming. And as I mentioned earlier, that is our main goal. So with the protein engineering, the first thing we had to do is go in there and remove the amino acids that are highlighted in red. So now we have our SBAFP with the end cap removed. But this protein still has a few problems. Mostly it has the amino acid cysteine, which has a specific functional group that can be highly reactive and under problem in the lab. So we actually mutated those cysteines to serines, and now we're left with a very highly regular protein, but it's small. And just for ease of handling in the lab, we decided to double that protein. And so we have our SBAFPM1 fused dimer. Great, so now we have our idealized protein, but how are we going to make it form that protein polymer? So focusing in on the interface between two of the proteins, what we did is we went in and engineered partner amino acid residues across the interface. And these residues, these amino acid residues, will actually form salt bridges, so positive and a negative charge, and hopefully those salt bridges will help aid this protein self-assemble into a polymer. Just some quick fundamentals on proteins to make sure everyone understands what we're doing here. And so you see the central dogma of biology here. DNA gets transcribed to RNA, which gets translated to proteins. And this phenomenon actually happens in all living organisms. And one organism that we can take advantage of as scientists in the laboratory is E. coli. We can have E. coli serve as small factories for us. So knowing the central dogma and knowing that we can go forward, where protein engineering really comes in is being able to go backwards. So we have this protein that we designed on a computer, and knowing this dogma, we can back translate and back transcribe back to its DNA. Once we have the DNA, which is the gene that encodes for the protein, we can insert that DNA into E. coli and then induce protein expression. So this is recombinant protein expression. It's done in various different labs all over the United States. And just in general, there's mostly two types of proteins out in the world, globular and fibrous proteins. And so here's an example of a globular protein. It has a very specific function. Its structure is a lot more complicated. And then we have fibrous proteins. And so here's an example of collagen here. It's proteins that tend to form sort of like fibers. And the proteins that we decided to work with are solenoid proteins, and those are sort of in the middle of globular and fibrous. So they're highly regular, and you can imagine they look like wire coils. And so we went ahead and did the protein engineering, did the recombinant protein expression, and the easiest way to view these protein polymers is through AFM images, or atomic force microscopy. And so here what you can see are these really beautiful protein polymers. And they range anywhere between 500 nanometers to 2 to 3 microns. And one individual protein that I showed you earlier is only 5 nanometers in length. So if we take this 1 micron protein polymer, it's made up of 200 protein subunits. And so this is definitive proof that through the engineering that we employed, we were able to make these protein polymers. And with AFM, you can actually do height analysis of these proteins, which are these height structures here, and the height seen experimentally matches the theoretical height that was calculated during the simulations and protein engineering. And so this image that you see here is actually the same protein sample, but it has been aged for a month. And so what that really shows is the stability of these protein polymers. And there appears to be some higher order structures appearing, possibly some lateral assembly. And so now the next step of this project is really to functionalize these proteins. And there's a few different ways that we can do that. The first one would be through peptide extensions. And so this would go back to the protein engineering, and we would add in specific peptides that are known to bind to inorganic materials into the DNA of the protein, go through the recombinant protein expression, and then be able to produce this protein here. Once it has the peptide, we can then add in the nanoparticles that the peptide should capture, and now we have a functionalized protein polymer. Another way of doing that is through chemical modification. So we can go back into the protein, mutate a few of the amino acids to have a specific reactivity through a functional group. And here I'm showing 2 cysteines, and we can use the cysteines to further functionalize the protein. We can add on nanoparticles, add on peptides, maybe even another protein, and that could then further functionalize the protein. And so these 2 examples are really more on a one-dimensional scale. We have some research going on currently going into higher order structures where we could potentially make 3D and 2D dimensional arrays using 2 different types of proteins, and then possibly having them into sheets. And what are the applications of this project? And the applications really depend on how you functionalize the protein. So imagine we have a protein polymer here. If you functionalize that protein polymer with a more inorganic material like gold, lead silane, or titanium oxide, then you really get into energy applications such as nanorods for optics, thermoelectric devices, solar cells, or photovoltaics. If you then take this protein polymer and functionalize it with a more biological aspect like an enzyme or a different peptide, then we can go into biological scaffolding, which could be used for tissue engineering or even biological labels. And the image that I showed you earlier with the 2D and the 3D matrices, now we can go into multi-component nanostructures that will allow us to go to novel optical sensors, perhaps have bioassays with multiple different enzymes at different locations, and that can really open up some devices for therapeutic materials. Really quick, I'd like to highlight some of the accomplishments of this collaboration. And so like it has already been mentioned, it's really a multidisciplinary collaboration that spans across the physics, chemistry, and electrical and computer engineering departments. And it's been really nice as a chemist to be able to meet all of these other professors and be able to talk about the research within the different departments. We have filed a patent for one of our designer proteins. A startup company is currently being started called Protein Architects. And we're actually going to be sponsoring a workshop with the Florida Agricultural and Mechanical University in May, later this year, for biologically enabled self-assembly. And we've been able to publish 3 papers. 1 paper is currently in review and is very likely to be submitted. Lastly, I'd really like to thank all of Team Answer for all of their support and all of the mentoring. Here are some current members and some former members, people that have graduated. And I'd like to thank you for your attention.
Any questions?
Thank you.
Well, thanks very much to the Chancellor and to the Office of Research for this program. And I'm pleased to be here for a little bit of an unveiling today of one of the outcomes of this collaboration. This project, which we've called Synergy for Consumer Energy Interfaces, was an idea to bring together computer science, behavioral research, and designers together to work on a problem which was communicating energy use to end users. We have a pretty big team of people working on everything. The original idea was really looking at dashboards of automobiles and thermostats and seeing how poorly some of these perform as interfaces for energy use. Also, laptops also not performing that well. So, okay. There we go. So I'm not going to say too much like that because Justin Woodjack is going to come up and explain the projects as a student, and this is really something students have taken off. This is something they understood right away as we began to present this to them as faculty, and they really have a diverse set of skills to really organize this area of research. And you'll see, I was picturing, dashboard graphical interfaces, and we are working with that, or computer interfaces. Sort of graphics is a big area of interface work. But actually, they've taken some things in some whole new areas, and we're getting into that behavioral research now. So without any further, I'm going to turn it over to Justin.
Welcome everyone. Thank you, Tom, and thank you all the Office of Research people for putting this on. Real quick, I'm going to take a selfie right now and tweet this a little later. If everyone, my favorite is Hang Loose if you like peace, or also maybe this year, Live Long and Prosper would be a good one. So if y'all want to get in there, great, thank you everyone. So I'm a PhD student under Tom's awesome guidance. And I just really want to take a moment to appreciate him and everyone else in our group because sort of I think you've been getting a flavor of what's special about some of these RISE groups is this interdisciplinary, but for us too, it's really like a family. One of the biggest things that has come out of this for me is a lot of good friendships, as well as a lot of life experiences about just growing outside of my own discipline and gaining some new perspectives on life. So it goes beyond the research to me. So I'm really passionate about this and the project, mainly because there's just a really fun group of people behind it. So a lot of the things you'll see here, it's a whole group behind me. So, but that being said, let's start with me. I love my life. This is me last Friday. The opportunities that I've been able to get through this program, ITS with Dan Sperling and Tom Turntime. This is the autonomous vehicle Mercedes unveiled at I think the Vienna Geneva Auto Show. We got to go out in Alameda test track and drive it around, and it was amazing. For me, someone trying to understand how we're going into the future with technology, and especially with interfaces and a lot of automation, right? The Nest thermostat, there's a great way of automation in the home, something we're looking at. And we're starting to see how a lot of these companies are failing in keeping the human in the loop. I've even heard a lot of personal situations where the Nest in particular, it's doing all this sophisticated learning and algorithms, but yet the user feels lost, feels unconnected, out of the loop. And in this vehicle was great for me opportunity to go and actually start seeing how these companies developing these technologies and implementing these systems are thinking about how are they interfacing and hopefully keeping humans connected with those systems. Energy is huge, and we're trying to tackle this mainly through consumer energy interfaces. So looking through the human side of everything. And more recently, as Katei and others have been talking about, the dynamic component of this team, I'll get into in a little bit, you'll see it is changed over the last 3 years. Where we've started, where we've come now has been really impressive. And we're even now starting to look out beyond just energy. Because for sustainability, for this earth we live on, which I'm really passionate, hopefully keep living on without too much climate disaster, it's more than energy. Here in California, water is a big one. So we're starting to also look on campus. The UC Davis water tower, we're trying to see if maybe we can help retrofit it with LEDs and help it be a beacon of water consciousness in this state. Sort of, we have all these goals as a community, whether that's Davis, UC Davis here, we all have our own goals. 2025, we're going to try to be zero net, as well as state of California has its own goals. So how can we get everyone on board? We can't do these goals just by, how many of the people in this room know how far along in progress we are toward meeting our 80 and 2050 goals? Are we doing good or are we not? Sometimes these simple questions and what you need simple answers to make proper decisions, whether that's a policymaker or a consumer. So this is some of the flavor of what we're doing. And I think it was great just hearing earlier today. It really is true that some of these endeavors that these initiatives have started out on, it's unclear maybe where we're headed, where we're really going to end up. But we're ambitious. We're going in that direction. And this is Don Norman, a great designer, human-centered designer. And really, if the product is truly revolutionary, it's unlikely you're going to do it right the first time. So we got together and we've been looking at energy interfaces and what is the current state of affairs? What are a lot of systems looking like? A lot of charts and a lot of graphs. Okay, map. I love maps. I'm a geographer nerd, but some of these, how you implement them, it really makes a difference of their impact and engagement with people. So, not pointing names or anything, but some other schools, they're just putting information up on a screen, and that's great. There's a lot of great web systems to be able to interface with data and look at it, but as Tom said, can you connect with it? Does it feel meaningful to you? Do you feel motivated now to go and do something? Change your behavior, do better. So this is our office. We're over in West Village. We have some beautiful office space where primarily students and some grad students and postdocs have been really taking in The camaraderie around this group is really fun. And we started looking at these and thinking, well, how can we do better? And it's been a long process. Here are a few of some of the students' projects, trying to rethink how can you communicate in semantic, very natural language, information, energy information. And we're actually, this is a new endeavor where an energy interface you can witness outside. We're starting to actually generate our own algorithms and our own semantic computer engines, so all this computer AI learning. We're trying to put human language into those systems to take that data and translate it into processable and meaningful, and hopefully a little playful too, information. So here I just want to reflect on iteration of design and experience. This is early, the interface you'll get to witness today on the right. This is our first gen on the left, working the very first time. Glenda drew out of the design department, her interactive design class had a bunch of student projects, and this came out of it. A few of the students came into our group and stuck around, and we've been able to improve and iterate on it. The hardware as well, we didn't have any mechanical, electrical engineers at the get-go, but we brought them on, and through design, we've been able to weld and actually take advantage of the machine shop and build our own energy monument, tangible computing. Before, we didn't have the know-how, we just had these ideas. How could you get a building, perhaps, or a campus to express its energy data? We didn't know. So you see on the far left, we have some, me using my table saw, and we had one intern from Sacramento who knew little Arduinos, and so wow, he allowed us to do a very simple prototype, and okay, working with Josh Morjon on campus, and sort of getting some more students on board to help us get a little bit bigger iteration. And finally, you see here now this human scale tangible feedback, which I really encourage you to go and experience. And there'll be a few of us out there. I'm not going into detail now about how it works. But there again, these are some of the faces. These are the people that I've come to really appreciate and enjoy in the work. I've learned how to be collaborative. I've also really had an opportunity to learn how to step outside of my comfort zone. It was great hearing earlier this notion of being able to go outside your comfort zone with regards to big ideas, maybe ones that fail. It's unclear. Sometimes you're working hard in the lab late, wondering, is this going to work or not? So the team and the camaraderie you learn together is really big. I just want to thank you, and any quick questions, and also later I'll be outside to talk to anyone. But thank you.